In our next section, we're going to discuss the synthesis of ethers. The first synthesis we're going to look at is a named reaction called the Williamson ether synthesis. It is one of the first systematic organic chemistry reactions that was ever studied. It was discovered around 1850. In this reaction, what we do is we start with an alcohol that contains one of the two carbon groups we want from the ether. We treat that alcohol with sodium hydride, which is a reaction we discussed in chapter 11. We then treat the product of that, which is an alkoxide, as we'll see below, with another alkyl halide, R'(X). This is going to perform an SN2 reaction. The X is going to be a leaving group, either chlorine, bromine, or iodide. And the R' group is called R' because it can be a different carbon group from the one on the starting alcohol. However, the R' group is going to have to be unhindered, so it will either have to be methyl or primary because we want to do an SN2 reaction. The mechanism for this reaction is shown here. In the first step, we use sodium hydride, which is a strong base, to deprotonate the alcohol. The hydride ion makes a bond to the hydrogen of the hydroxyl group. A pair of electrons on the other side goes on to oxygen. We're left with what we call an alk oxide ion. That alk oxide ion will be paired up with the sodium spectator. In step 2 then, we add the R'(X) SN2 substrate. The alkoxide becomes a nucleophile. It performs backside attack on the R' carbon, pushes out the halide, and we are left then with this molecule, which is an ether. There are two important facts I want you to know about this. First of all, sometimes we can have the alkoxides available from other sources. In that case, then, the sodium hydride step can be skipped, and we can just add the SN2 substrate directly. And second of all, as mentioned before, because alkoxide is a strong base nucleophile, we're going to be limited in our choice of the alkyl groups on our substrate. It's going to have to be an unhindered group like methyl or a primary carbon. The next synthesis reaction we're going to look at is called Alk Oxymercuration Demercuration. That's a name that should look kind of familiar. We studied oxymercuration demercuration in an earlier chapter. In Alk oxymercuration, we do the same basic reaction as oxymercuration, but instead of using water as a nucleophile, we use an alcohol. So water would have HOH, and we would produce a hydroxyl group in our product. In Alk oxymercuration, we use ROH, and at the end, we have attached an OR, an alkoxy group, to our product, making an ether. I'm going to review the mechanism of this very quickly. It's extremely similar to the oxymercuration demercuration mechanism, but we're going to use ROH instead of HOH. So in the first step, the alkene reacts with a mercury 2 ion. The pair of electrons from the double bond comes out and makes a bond to the mercury, but because the mercury is so big and because it has d electrons, it uses some of those electrons to make a bond to the other carbon, which would otherwise be a carbocation. This forms this ring, which is called a cyclic Mercurinium ring. The mercury is in a three-membered ring and it has a positive charge on it. Because of the positive charge, these bonds are very polar and the carbons have partial positive charges. So they can attract a molecule of nucleophile, in this case the alcohol ROH. A pair of electrons will come over and make a bond to one of the carbons and push the mercury bond back onto the mercury, forming this intermediate. In this intermediate, the oxygen, which had two groups on it when it attacked, now has three groups attached, and it gains a positive formal charge. Ideally, the molecule would like to lose this formal charge, and so a base in the system will deprotonate this positively charged oxygen. By removing that hydrogen, a pair of electrons will go onto the oxygen, and we end up with this molecule, which has mercury attached to one carbon and our desired alkoxy group on the other carbon. We would prefer not to have the mercury. These molecules are actually quite toxic and explosive. So, in a second step, we add sodium borohydride, which replaces the mercury with hydrogen. We will not be giving the mechanism for this. It is a free radical mechanism. We do not need to know that. You just need to know that it replaces mercury with hydrogen, and that gives us our final product. This reaction proceeds with Regio Selectivity. It follows Markovnikov's rule. Furthermore, there is no carbocation intermediate, so there is no rearrangement. Here's an example showing how the Regio Selectivity works. If we take this alkene, which has two carbon groups attached to the left carbon and only two hydrogens attached to the right carbon, we treat it with mercury acetate and this alcohol. What will happen is the hydrogen will become attached to the carbon that has the most hydrogens. In other words, the less substituted carbon, which would be the right-hand carbon. And the alkoxy group of the alcohol will become attached to the more substituted carbon, which is the left carbon. That creates this product right here. We're now going to look at the reactions of ethers. In general, ethers are relatively unreactive, with the exception of epoxides. For this reason, ethers are really excellent solvents because they can be used with a variety of reagents and not do any side reactions. However, they are unstable in strong acids. So we can use that fact to do a reaction on ethers and cut them apart. Therefore, we're going to look at a reaction called acid-promoted cleavage of ethers. In this reaction, we're going to start with an ether, which again can be generalized as a carbon group attached to an oxygen attached to another carbon group. The two carbon groups do not have to be the same, so therefore I've put a prime on one of them. What we're going to do is we're going to use hydrogen halide, where the halide would either be bromine or iodine. And we're going to use an excess so that we can get as much reaction as possible. At the end of this reaction, we're going to see that the two carbon groups have been cut away from the oxygen, and the oxygen has been replaced by the halogen from the hydrogen halide. This mechanism ties together a couple of the mechanisms that we learned in first semester. the actual preferred mechanism is going to depend a lot on which groups are attached to the oxygen. The first step in any case is going to be an acid-base reaction between the oxygen of the ether and the hydrogen halide. Hydrogen halides are extremely strong acids, so this will be a fairly favored reaction, and we will end up with an intermediate that looks like this, where that oxygen has been protonated and it has a positive formal charge. In this case, then, the oxygen, the hydrogen, and one of the carbon groups will act as a leaving group. I've decided to use the left carbon group as part of the leaving group and have the subsequent reaction occur on the R prime. That means that the R prime is going to basically determine which mechanism this follows. If the R prime is methyl or primary, then we have a very good leaving group attached to a methyl or primary ion, carbon, and we have a good halide nucleophile. So the nucleophile will do an SN2 reaction. It'll make a bond to the R prime carbon group, and it will push out the ROH as a leaving group. So we would get these two products. We're going to see that the ROH, in many circumstances, is going to continue reacting. On the other hand, if R prime is secondary or tertiary, SN2 reaction is going to be disfavored, and instead it will do an SN1-like reaction where this alcohol leaving group will break off from R prime, we will get a cation, and then X will react with that cation to form this product. Again, the alcohol product can continue to react with the hydrogen halide. So if we have formed alcohol product, then that can come over and that can react with the hydrogen halide according to a reaction that we learned in chapter 11, which results in replacing the hydroxyl group with another halogen. One complication then is that certain alcohols, for example, phenyl alcohols, which we call phenols, cannot be converted to the halide by HX because they don't do SN reactions. As a result, what we will see in that case is if we have a phenyl ether, which has a carbon group, an oxygen, and then a phenyl directly attached to the oxygen, the non-phenyl carbon group will be R prime. It will react according either SN1 or SN2, depending on its degree of substitution. And the phenyl, the O, and the H will end up being the leaving group, making phenol, or if there's substituents on the phenyl group, a substituted phenol. The reaction will stop there, and we will get an alcohol plus the halide, because phenol cannot react by SN reaction, and it can't be converted to a halide by HX.